All right, let's dive into integration. Now, I know that word can sound a little intimidating, but I want you to think of it like a puzzle. It's actually the reverse of something you probably already know. Imagine we've been handed the final picture, and our job is to figure out what the original pieces looked like. So, let's get started.
So we've all spent a good amount of time with differentiation, right? Finding the gradient, the slope of a curve at any point. But what if we flip that whole problem on its head? What if you already have the slope, and you need to work backwards to find out what the original curve was? That's the big question, the central mystery we're going to solve today.
And you know what? The key to solving this mystery is actually surprisingly simple. We're just going backwards. We are literally going to reverse the process of differentiation that we're already familiar with.
Okay, so what does going backwards actually look like? Well, it's pretty straightforward. If differentiating a function gives you its slope, then integrating that slope takes you right back to the original function. But wait a second. Look closely. There's a new character in this story, this mysterious plus c. Don't worry, we're going to get to what that's all about in just a minute.
Think of it like a two-way street. It's super simple. On one side, we start with a function, say x cubed. We differentiate, and that takes us down the road to its slope, which is 3x squared. Well, integration is just the journey back. It takes that slope, 3x squared, and leads us right back home to where we started.
So now we get the big idea. Integration is just going backwards. But how do we actually do it? Let's talk about the first and, honestly, the most fundamental tool you're going to need.
And here it is. Meet the power rule for integration. This is going to be our first major clue for solving this whole reverse engineering puzzle. You could call it the workhorse of basic integration. You're going to use it all the time.
And here's the rule itself. It's basically a simple two-step dance. Step 1, you add 1 to the power. Step 2, you divide by that new power. That's it. Now about that mysterious plus c. Think about it for a second. The derivative of x squared is 2x, right? But what's the derivative of x squared plus 5? It's also 2x. The derivative of x squared minus 100? Still 2x. Any constant number just vanishes when you differentiate. So when we go backwards, when we integrate, we have to add that plus c to stand in for any possible constant that might have been there.
Okay, let's put this rule to the test. First things first, before we can integrate, we've got to prep our terms. You see that fraction with the square root on the bottom? We can't really work with that as is, so we rewrite it in power form as 5 times x to the power of negative 1/2. Perfect. Now we can apply our simple two-step rule to each part. Add 1 to the power, then divide by the new power. And of course, what do we do at the end? We always finish by adding our constant, plus c. Don't forget it.
Now, the power rule is amazing. It's a fantastic tool, but it's not going to solve every single problem. Just like a good detective needs more than just a magnifying glass, we need a whole toolkit for different kinds of functions. So let's start building it out.
So what happens if you've got something like 2x minus 1 all raised to the power of 5? Well, the process starts exactly the same as the power rule. Add 1 to the power, divide by that new power. But there's one tiny extra step. You also have to divide by a, which is the number in front of the x. It's a small detail, I know, but it's absolutely crucial to getting it right.
Let's grab our next tool, exponential functions. And you're going to love this one, because it is beautifully simple. The integral of e to the power of x is just e to the power of x, plus c, of course. And hey, if you have a linear function up in the power, like e to the ax plus b, that little rule we just learned applies again. You just divide by a, the number in front of the x. Easy.
All right, on to the trig functions. The integral of cosine is sine. Simple enough, right? But, and this is a big but, be careful with sine. The integral of sine ax plus b is negative cosine ax plus b. And yeah, we still divide by a. That little sign change when you integrate sine is a classic trip-up, so definitely make a mental note of that one.
And for our final tool, hey, remember how the power rule said it worked for n not equal to negative 1? Well, this is why. When you try to integrate x to the power of negative 1, which is just another way of writing 1 over x, you get something totally different, the natural logarithm of x, or ln x. And what do you know? For the linear form 1 over ax plus b, the same exact pattern holds. You get the natural log, and you just divide by a. Okay, so we have our toolkit, we're ready to go. But that plus c means that every time we integrate, we're not just getting one answer, we're getting a whole family of possible curves. So what if we need to find one specific curve? How do we nail down the exact value of c?
This is how we crack the case. If we're given an extra piece of evidence, a specific point that we know the curve passes through, we can pin down the exact value of c. The strategy is a simple three-step plan. First, you integrate like normal to get the general equation with plus c. Then, you substitute the x and y values from the point you were given. And finally, you just solve the simple little equation that's left to find out exactly what c is.
Let's see this whole strategy in action. We're told the gradient is a square root of 2x minus 7, and that our curve passes through the point 8, 11. Okay, step 1. We integrate using our linear power rule to get the general equation. Step 2. We substitute our known point. So, 11 goes in for y and 8 goes in for x. Now all that's left is a bit of algebra to solve for c, which in this case turns out to be 2. And just like that, we've gone from a whole family of curves to the one specific equation we were looking for all along. Phew, that was a lot of new tools for our kit, right? So let's do something useful. Let's bring them all together into one master key. Basically, a cheat sheet that summarizes everything we need to solve these integration puzzles. And there you have it, your complete integration toolkit all in one place. We've got our workhorse, the power rule. We've got its cousin, the rule for linear forms. And we have our special tools for exponentials, for trig functions, and for logarithms. This right here is the core takeaway. Everything you need to get started reversing the process and finding that original function. So, when you really boil it all down, integration is way more than just a mechanical process in math class. It's a way of thinking, really. It's all about reconstruction. We're starting with the pieces, the rate of change, the slope, and from that, we rebuild the whole thing. And that kind of makes you wonder, doesn't it? If we can rebuild an entire function from just its slope, what else in the world could we rebuild if we just took the time to understand its component parts?